All right, so good evening and welcome to the sixth live session for Multirate DSP. In the week 6 of the course, um, we have continued the analysis of M channel maximally decimated filter bank, and specifically, we looked at the case for M equals to 2, and we saw the input output relationship in terms of the transfer function, and we saw that okay, in the transfer function we have a signal component as well as an aliasing component, and we want to get rid of the aliasing. And what are the conditions for that? What are the conditions on the synthesis filters and the analysis filters that we need to take into consideration in order to remove the aliasing? And we also saw certain other criteria of filter design, other aspects of filter design, like the allowable deviation in the pass band, allowable deviation in the stop band, and the flatness constraint, and so on. Finally, we also looked at the quadrature mirror filter, QMF for short, and so yeah. So keeping these ideas in mind, let's get started with today's session. Okay, so I hope you can see the first question on the screen. So please give it a read. So for today's session, mostly all the questions are straightforward and pretty much simple if you have gone through the lectures. Okay, so what we are asked in the first question is as follows: which of the following is or are the conditions for a type 1 linear phase filter of order capital N? So this is straight away a factual information which was also discussed in the lectures. So you can straight away mark the right answer if you are aware of it. So anyways, I'll go through it. So let me switch to the other tab. We are discussing contents related to week 6. Okay, okay. So I'll go through the problems one by one, and please feel free to interrupt me in case you have any queries. If there are no queries, then I'll assume that everything is fine. I'll just proceed in my own pace. So start with the first question. Okay. So yeah. So which of the following criteria applies for a type 1 linear phase filter, particularly an FIR filter? So with an order capital N. So we have seen this, right? So what we are looking at essentially here is a linear phase FIR filter. So here by filter in the question we are explicitly meaning referring to linear phase FIR filter. And in case you need to uh, brush up these concepts, you can just go back to your lectures or refer to the textbook. So I'll just make a note here, refer to lecture 22, or you can refer to the textbook, which is the textbook by Oppenheim and Schaffer. Okay. All right, so what we are going to do is, so let's say we have an impulse response. So here we are given that I'll go back to the question. Here we are given that the order of the filter is capital N. Okay, and it's a type 1, it has to be a type 1 filter. So what do we mean by order of a filter? Okay, in general, we have the impulse response of the filter, which is given by small h of n. Okay, this is the impulse response. We use lowercase for impulse response and uppercase uh, for the frequency response, right? So, or the Z transform. So this is in the time domain. So h of n, let's say, has the following samples. So let me keep it to be a causal filter starting at the index n equals to 0. So the corresponding value would be h of 0. Okay, is there any question?
No, sir.
Okay, okay, I thought there might be a question, but okay, so let's continue. So yeah, so and corresponding to the index n equals to 1, there would be the value h of 1 and so on till, since the order is given to be capital N in the question, the last term would be h of capital N. This is the impulse response. And if you want to uh, look at the Z transform of it, so h of n has a Z transform which is given by capital H of Z. Okay, so Z, and we know the expression for capital H of Z. It's simply summation, right? Summation over n, h of n, z to the power minus n. Okay, summation over n. In this case, n actually runs from, small n runs from 0 to capital N. Okay, because capital N corresponds to the last index. So this is a finite impulse response, right? Finite length impulse response. That's why we call it an FIR filter. It's not infinitely long, it has a finite length. And note here is that the order of the filter is capital N, whereas the length of the filter is 1 greater than the order, which is n plus 1. Okay, okay, so this, and so what is your h of z? H of z is, so we already know the answer for this question. I'm just giving you sort of a revision for this. So if you expand this summation, what you are going to get is this, so on till the last term would be this. Okay, so here we call that the order of the filter. Whenever we design the filter, this order is a very important thing. We have to choose, we can't just randomly choose any order, so the order has to meet certain criteria, right? So this order of the filter here is your, this capital N, this parameter. Okay, the highest degree you can imagine, like, okay, the last term here, this term has z to the power minus n, right? So that n is your order of the filter. Okay, and if you see how many coefficients are there, how many terms are there, so these are synonymous terms. Number of coefficients or number of taps or the length of the filter, all are same. So that that is equal to n plus 1, right? Because it starts at the index 0 and ends at the index capital N. So altogether there will be n plus 1 coefficients, okay, which is your length of the filter. So number of coefficients, which is equal to, also known as sometimes number of taps, is also known as the length of the filter, is 1 greater than that. So 1 greater than the order, which is n plus 1, clearly. Okay, great. So now you can go back to lecture 22, which I already mentioned, or you can refer to the textbook, where you can find a table which actually uh, demarcates the 4 different types of linear phase FIR filter. So there are 4 types: type 1, type 2, type 3, and type 4. And what are the characteristics of those 4 types of filter? So I'll make a table like that. So the first column is the type of the filter, okay. Second column is the order, which is capital N. Third column is the length, which is, we just saw, 1 larger than the order, which is n plus 1. And there is another property, which is the symmetry of the impulse response that we are looking at, okay. Symmetry of h of n, or the impulse response. So these are the 4 columns and will form a table. So first is a type 1 linear phase FIR filter. For a type 1 filter, we must have the order to be an even integer, okay, and the length. So what if capital N is even, then the length, which is capital N plus 1, would be an odd odd quantity. That's evident. So this will be odd, okay. And the symmetry of the impulse response should be even symmetric, okay. The impulse response should be even symmetric. You know, right, what's even symmetry? What does it mean? So it means like uh, it is symmetric about the center, okay. So in other words, h of n, small h of n, is the same as small h of capital N minus small n for all small n between 0 to capital N. So you can see that, okay, the first and last coefficients would be the same, the second and second last coefficients would be the same, and so on, okay. So you can see it forms a mirror image about the center, okay. Okay, so this is type 1, and similarly for type 2, what we have is the order would be odd, which automatically implies the length would be even, and the symmetry also has to be even, okay. Then we have the type 3, which is even order and odd length, and also the symmetry has to be odd. The impulse response is odd symmetric. Sometimes we also call it anti-symmetric, which means that h of small n is equal to h of minus of h of capital N minus small n for all small n between 0 and capital N. So it's like, since it is odd symmetric, it's very similar to the even function and odd function, right? That's what you have there. So the first coefficient here in odd symmetric impulse response, you can think like the first coefficient and the last coefficient, they are same in magnitude but opposite in sign. Okay, if the first coefficient is +1, the last coefficient would be -1. Similarly, the second coefficient and the second last coefficient would have the same magnitude but opposite sign. Let's say one is +2, the other one would be -2, and so on. Okay, right. So, and finally we have the type 4, which says the order should be odd and the length should be, automatically the length would be even, and the symmetry again here is odd symmetry of H of n. Okay, this is a table which is important. Okay, we have seen this in our lectures as well. Okay, and now going back to our question, we are asked like, what is the condition for a type 1 linear phase FIR filter of order capital N? So if you just check the condition for type 1 and order capital N, it is an it has an even symmetric impulse response. The first, so we are corresponding to the first row of this table. So that's the type 1. So even symmetric impulse response and odd length, you can see, right? So odd length, and also the order is even. Okay, so the first row we are seeing. So even symmetric impulse response and even order, both are even. So which option satisfies that? I think it is option D, even symmetry in impulse response and even order, right? So the answer is option D. Okay, simple. Okay, great. Okay, right. So now moving to the second one. So I'm assuming it was straightforward, fine. Okay, now read the second one. In the second question, we are given that capital H naught of Z is a type 1 linear phase filter. We just saw what's a type 1, what are the conditions for a type 1 linear phase filter in first question. Now in second question, we are given that capital H naught of Z is a type 1 linear phase filter. Then its QMF pair will be what? Of what type? Whether it's type 1, type 2, type 3 or type 4. And QMF, you should be familiar with the full form of QMF by now, which is Quadrature Mirror Filter Bank, right? So this is the um, full form of QMF, Quadrature Mirror Filter. So we have seen, right? We have seen, okay, when does, a pair of filter become a QMF pair? What's the condition for that? Basically, if you have H naught of Z, then the other one should be H naught of minus Z, or in other words, a shifted version of the original filter, shifted by pi, shifted in frequency by an amount of pi. We have seen, okay, and both of the filters are actually symmetric about the point which corresponds to omega equals to pi by 2. That's why pi by 2 is known as the quadrature frequency actually, and pi by 2 is nothing but 1/4 of 2 pi. So 2 pi is your sampling frequency, so 1/4 of that is the point of symmetry. That's why it's known as quadrature. Okay, quadrature frequency. Okay, right. So okay, so now the observation here is that you are given that H naught of Z is type 1, and we just saw in the first question that type 1 implies that the impulse response should be even symmetric and the order should be also even. Now its corresponding QMF pair would be H naught of minus Z. We have seen these in the lectures because it's just a shifted version of that, right? And why do I say that H naught of minus Z is a shifted version of H naught of Z? Basically, if you replace Z by e power j omega, then H naught of Z becomes H naught of e power j omega, and H naught of minus Z is equal to H naught of minus e to the power j omega, which is also same as H naught of e power j omega minus pi. So it is the same thing as shifting your frequency by an amount pi. Okay, the filter remains the same, you just shift the filter. Okay, so those two filters form a QMF pair. Okay, so we have seen all these things, right? Now what is the type of that uh, H naught of minus Z, the its QMF pair? So clearly if you shift the original filter and you get H naught of minus Z, then by property of Z transform or using the property of DTFT, you can claim that its corresponding impulse response would be minus 1 to the power n times H naught of n. Okay, so which means that I'll show it how we can do that simply using the property. So minus 1 to the power n H naught of n. So which means that if you vary n for all even values of small n, the filter coefficients remain unchanged, whereas for all odd values of small n you get a minus sign, the coefficients get flipped. Okay, but even if you do that, because H naught of n is originally a type 1, so it's even symmetric, even if you do this minus 1 to the power n times H naught of n, it still remains symmetric, it still remains even symmetric. That's the point. And so yeah, so and of course the order also remains the same, the order is not changed. Okay, you're just shifting your filter, that doesn't change your order. So the order as well as the symmetry of the impulse response both remain even, and it still stays as a type 1 filter. So we already have our answer, which is A. Okay, now if I have to put it down on a note, so I'll just mention. Okay, so this, since H naught of Z is type 1, they are given, we know that it's from the property of type 1 FIR filter, linear phase FIR filter, its impulse response has even symmetry and the filter has also got even order. Okay, remember that capital N, that is also even. Okay, and now well, what does a QMF pair look like? So we have seen a diagram like that. Okay, so imagine you have, sorry, something like this. um, let's say this this is let's say your H naught of Z, which has a low pass rate. Okay, this point is 0, of course. Then its corresponding QMF pair would look something like this. This, okay. This point is sequence here. So, and this point of symmetry actually is a different color. So this point, this frequency here is pi by 2, and we are looking in the range of 0 to pi. Okay, fine. And this red filter that we have drawn is basically the QMF counterpart of H naught of Z. Together they form the QMF pair, and this red filter is H naught of minus Z. Okay, right. So we have seen this type of figure, and also this frequency, as I mentioned before, this pi by 2 is also known as your quadrature frequency. Okay, so quadrature mirror filter, or QMF for short. So quadrature mirror filter pair means if I denote the other filter as H1 of Z, then H1 of Z is basically, we just saw, and I have also drawn the diagram, that it is equal to H naught of minus Z. Okay, right. So now you can take the inverse Z transform on both sides, which will actually give you small h1 of n, which is equal to minus 1 to the power n times small h naught of n, using the property of Z transform. Or also you can evaluate Z at e to the power j omega and take its inverse TTFT, which will also lead you to the same result, which is h1 of n. The impulse response of the other filter is nothing but a minus 1 to the power n times the h naught of n. So so both the ways are fine. So okay, so if I label this by equation 1, okay, then taking the inverse Z transform on Z transform on both sides of equation 1, we get h1 of n. In the LHS we will get h1 of n, and on the right hand side we will get minus 1 to the power minus 1 to the power n small h naught of n. Okay, that's how their corresponding impulse responses would be related. And in case you are figuring out how did we get this, how did we arrive at this, what we are doing is, I'll just mention it in a bracket, that we know this property of Z transform, that if we have some a power n x of n, okay, that has a Z transform which is equal to capital X of Z by n. Okay, so if you put putting a equals to -1, what do we have? -1 to the power n x of n has a z transform equal to capital X of minus n. Okay, so you see it's the same form that appears in equation 1, and we can claim that the impulse response is simply -1 to the power n times the original impulse response. Okay, good. So okay, yeah, so I'll just go to the next page. Okay, and by the way, the standard notation that we use is like small h naught of n has a z transform denoted by capital H naught of z, and small h1 of n has the z transform denoted by capital H1 of z. So this is the standard notation that we use. Okay. So now we saw that h1 of n is expressed as in terms of h naught of n as follows. It's like this. We just saw it. Okay. So what I claim here is that it doesn't alter the symmetry of your original uh, h naught of n. If h naught of n is originally even symmetric, which is the case because in the question you are given that h naught of z is a type 1 filter, it should have an impulse response which is even symmetric. Even after doing this transformation, doing this -1 to the power n times h naught of n, it still remains an even symmetry sequence. That's what I'm claiming. And also the order remains the same, because if you are simply just shifting the coefficients, okay, so the order remains the same. Okay, and the order, I mean the order still remains even. That's what I mean. Okay, so if you try to visualize this, h naught of z, I'll rewrite it. H naught of z is type 1. This is given. This is given in the question, which automatically implies that its corresponding impulse response, which is small h naught of n, has even symmetry. We saw the table, right? And also it has even order. Okay, and if you try to expand this express this as a summation, h naught of z is simply h naught of 0 at the index n equals to 0, and similarly at n equals to 1 we have this delay term coming into the picture. Similarly, h naught of 2 to the power -2, so on till h naught of n minus 2, z to the power minus of n minus 2. Okay, and we are using capital N to represent its order, so it will go till h naught of capital N. So the second last term would be h naught of capital N minus 1, z powered minus n minus 1, and finally the last term would be h naught of capital N, z to the power minus n. And where, so this is the entire summation, okay, form of h naught of z, which is your type 1, where since it's a type 1, n, which is your order, has to be even. We just saw from the table, right? Since type 1. Okay, and on top of that, we also have a constraint on the symmetry of the impulse response for a type 1 filter, that it has to be even symmetry. So also by even symmetry of type 1, this H naught of small n is the same as H naught of capital N minus small n for all small n running from 0 to capital N. That's what I mean. So meaning that if you look at this first coefficient here at n equals to 0 and the last coefficient here at small n equals to capital N, both of them should be equal. Similarly, if you look at the second last coefficient, which is small h naught of 1, and similarly if you look at the second last coefficient, which is this small h or small h naught of capital N minus 1, they should be equal, and so on, it continues. So and similarly this one as well, this term and this term, I'm using the same color to indicate that they are equal, okay, just for a visualization. So this is the condition of even symmetry. And now if we apply this constraint of even symmetry on the expression of h naught of z, what do we get? Therefore h naught of z is, okay, the first term is h naught of 0, okay, the second term is h naught of 1 plus h naught of 1 times z inverse, the third term is h naught of 2 times z to the power minus 2, so on till now. This, what about h naught of n minus 2? So we just saw that by property of even symmetry, h naught of capital N minus 2 is the same as h naught of 2. So this now becomes h naught of 2 by even symmetry, this. And similarly the second last coefficient, which is h naught of capital N minus 1, that again is the same as the first coefficient by even symmetry. So this becomes h naught of 1 z to the power minus n minus 1, and similarly the last coefficient, which is h naught of capital N, is the same as the first coefficient, which is h naught of 0 times, of course, times z power minus n. So you see the, okay, so this is what even symmetry and order n, which is some capital N equals to even, n is even, I'll again mention n is even. So this is the form, okay, of the filter for a type 1 filter. Okay, great. So if you look at it, look at its impulse response, so basically the filter coefficients, the first one would be index at index n equals to 0, this term. So similarly at the second index n equals to 1, we have h naught of 1, then we have h naught of 2, so on till h naught of 2, then h naught of 1, and finally h naught of 0. Okay, clearly this is a even symmetric impulse response, and overall its overall length, if you see, the length is capital N plus 1. because the order is capital N, which is an even number, so the length is 1 greater than that, so the length has to be an odd number. So this, if you represent it pictorially, you can verify that it's indeed a even symmetric impulse response. So at n equals to 0, let's say we have a point like this, it is equal to, the value is h naught of 0. So this is at n equals to 0. Similarly, at n equals to 1, we have h naught of 1. Let's say it's somewhere here. So at n equals to 1, we have h naught of 1. Similarly, let's say at n equals to 2, we have h naught of 2, which lies somewhere here. Okay, and it continues, so on, dot dot dot, at the index capital N minus 2, we also have h naught of 2 as the value, okay, as the coefficient. And on the immediate next index, which is capital N minus 1, we again have h naught of 1, and finally at the last index or nth index, we have h naught of 0. Clearly you see that there is a symmetry. Okay, this is even symmetry. Even symmetric, right? So now what happens is, maybe I should go to the next page. Now we have seen that h1 of n is nothing but minus 1 to the power n times h naught of n, which I already mentioned that what's happening here is that, so for all even values of small n, h1 of n is the same as h naught of n, whereas for all odd values of small n, h1 of n is simply equal to minus of h naught of n. Okay, so basically, yeah, what's happening is that all even index samples, okay, are remaining unchanged, whereas all odd index samples are getting flipped. So this you can, also express as the same as h naught of n when n is even, and it is simply minus of h naught of n when n is odd. Okay, so therefore clearly our h1 of n would just have, alternating minus signs. Okay, but the magnitudes of the coefficients remain the same. So the first one for h naught of n was h naught of 0. That's an even index. That's why it remains the same. And similarly, the next term was h naught of 1. But since this is an odd index, we will have this minus sign coming here because of this minus 1 to the power n term. And similarly for the next index, n equals to 2, again it's a even index, so therefore no flipping of sign, and we can continue. The third last coefficient would again be h naught of 2, because the index is even, because it is capital N minus 2. Capital N is even, so capital N minus 2 is also even. Therefore, the sign doesn't change. For the second last coefficient, it is capital N minus 1. N is even, therefore capital N minus 1 is odd. So there is a negative sign here. And also the last term, it's an even index, so no change of sign. Okay, this. So again you see this, it still stays as an even symmetric impulse response. This is your of length, again capital N plus 1, but it still remains even symmetric, because if you try to visualize it, h1 of n, let's say this is okay, this is the horizontal axis, let's say. Okay, so now, okay, yeah, so at small n equals to 0, we have h naught of 0. So you go back to the previous, this graph. At every odd index, we will just flip the sign of the corresponding sample value. Okay, that's what we are doing. So how does it look like? It looks like, and for the second, so this is for n equals to 0, and for n equals to 1, since it's a odd valued index, initially it was in the positive side, so now it will get flipped. Okay, there will be a minus sign. Maybe I should read out correctly, like this. So this would be minus of h naught of 1. This, due to this negative sign, it goes downward. So this is at n equals to 1. Similarly, at n equals to 2, okay, we had a sample like this. Okay, it still remains the same because it's a even index. So it will be somewhere here. Somewhere here. So this is at n equals to 2, h naught of 2. Okay, and continues all the way at index capital N minus 1. It still remains h naught of 2. Just look at the impulse response. We have written it here. All the alternating samples are just flipped. So at n minus 1, we'll have a flip. So this would go somewhere here. Okay. So this is again h minus of h naught of 1. This is at the index n minus 1. And finally at index n, we again have h naught of 0 index. Okay, great. So this again you see is indeed satisfying even symmetry. So, and of course the order also remains capital N. It's an even length, uh, even order filter. So therefore h1 of n also, which is the QMF counterpart of h naught of n, also has even symmetry. We just saw it, even symmetry, and same order, that is even order, or even order also means odd length, both are synonymous. So therefore, hence h1 of z, the corresponding filter in the frequency domain, is also, the properties are remaining the same, as that of a type 1 filter, therefore H1 of Z is also H1 of Z is also a type 1 linear phase FIR filter. Okay, so the type remains unchanged, so it is option A. So option A. Okay, all these, I've just shown. This stuff might be redundant, but yeah. Oh, fine. Hope you are able to follow. So now moving on to the third one. Hope you are with me. Okay. So this third one. Okay, third one, we have a block diagram here. Okay, and we have seen exactly similar block diagram um, while we were analyzing the two channel. This is, you see, there are two channels. So this is the special case of m equals to 2 for a two channel maximally decimated filter bank, right? So we have the analysis filters G naught of Z and G1 of Z on the left side, and towards the right end we have the synthesis filters J naught of Z and J1 of Z. I think in the lectures we have used a slightly different notation. I think instead of G we have used H, and instead of J we have used F. Doesn't matter, it's just a notation. So okay, what it says is that G naught of Z is equal to E naught of Z square plus Z inverse times E1 of Z square. So this is your type 1 polyphase decomposition. Okay, you have broken down your G naught of Z into two subfilters, and under the aliasing cancellation constraint. So first thing is aliasing has to be removed, has to be cancelled. So the aliasing term, which was A of Z, that has to be 0 under that constraint. And also using quadrature mirror filters, which of the following statements are right? Okay, we are given some expressions for the synthesis filters J naught of Z and J1 of Z in the options. We have to find out which one is correct, or whether multiple options are correct. So it's straightforward only. We have done the analysis. All these analysis were done in the lecture, so just go through them. And okay, I won't go through the detailed analysis step by step how we are arriving at the expressions, because that's completely redundant. So yeah, so this one, the third one. Okay, first I will draw the block diagram. Okay, x of n undergoes a branching. Okay, it is split, actually it is split. The input signal x of n is split into two components. So that's why these filters, this G naught of Z and G1 of Z, are known as analysis filters, because the signal is split into multiple components. Then we do downsampling, and we have this V naught of n, V1 of n. Okay, these are the intermediate sequences as labeled in the question. And on the other end we have, okay, upsampling by factor of 2, Similarly, on the second branch, we have this upsampler, and the intermediate sequence was labeled by y naught of n, and on the lower branch it was y1 of n. And now comes the synthesis filters, which was denoted by g naught of z. This is for the upper branch. So why synthesis? Because these filters are actually, combining the signal components together to form a single signal. So this is getting added. I'll use arrow, okay, consistently to indicate the direction of the flow. So this arrives at a adder here, which produces or synthesizes our output x hat of n. The goal is to, recover x of n, which was our original input, from this uh, output x hat of n. So x hat of n is kind of an estimate of x of n. We want uh, to ensure that, okay, from x hat of n we are able to still recover our original input sequence, which is x of n. Okay, so this is the block diagram, and now we are given that, okay, g naught of z has a type 1 polyphase decomposition. So this E naught and E1 are usually the notation which are followed, it doesn't matter, it's followed in case of the type 1 polyphase decomposition. And in the lectures, I believe R0 and R1, the notation capital R was followed for type 2 polyphase decomposition. So this I'll call as equation 1. And as a side note, I'll just mention that this is nothing but your type 1 polyphase decomposition. Okay. And okay, so and now just recall your lectures. We have actually derived the relation between the input and output. In terms of the Z transform, we have actually arrived at how the input and output are related in the Z domain through some overall equivalent transfer function. So we have seen that x hat of Z, so this is in the Z domain or frequency domain, capital X hat of Z is equal to some capital T of Z times your input spectrum X of Z, right, plus some undesirable aliasing term A of Z times capital X of minus Z. So this first term T of Z times capital X of Z. Capital X of Z is the Z transform of your actual input X of n. So that's your signal term. Okay. And the second term, this A of Z is actually the aliasing component. So this is your aliasing term. And you see it has a factor of capital X of minus Z. So that's a minus Z means it's a shift in the frequency. So we don't want that. That's a undesirable component. So that contributes to your aliasing term. We want to get rid of this. Okay. All right. We have seen this. We have seen this in our lectures. That's why I mentioned, just refer to the lecture notes. And where we saw that where T of Z was given by, so in the lectures I already mentioned that they had used some H, capital H instead of G, and capital F instead of G. So here just there's a slight change in the notation, otherwise the structure is the same. So T of Z has a form which is given by this, okay, and even if you don't remember this form, uh, it's a simple form actually, it's easy to remember also because there are only two branches, and even if you don't remember, you can anyways derive it as well. You can actually derive this intermediate sequences, what's the Z transform of that, and like we have done in our previous tutorials as well. So, and finally relate the final output x hat of Z with the input x of Z. So this was the T of Z component, signal component, the transfer function for that, and the transfer function of the aliasing component was half times J naught of Z, G naught of minus Z plus J1 of Z, G1 of minus Z. Okay, okay, it's already getting crowded there. I'll go to the next page. Now, in our question, we are asked, okay, first we need aliasing cancellation. So, aliasing cancellation constraint, which means that if you go back to your previous expression, it had a signal component and a aliasing component, right? X hat of Z. So, this aliasing term must vanish, which means A of Z times X of minus Z should vanish. And we can design, we can choose our filter such that this A of Z, because we don't have a control on the input, X of minus Z is the spectrum of the shifted input, we can't regulate that. We can choose our filters J and G such that this A of Z can be made 0, which can alleviate your aliasing term. So that's what we are going to do. So to cancel the aliasing, we need A of Z to be 0, and A of Z, the expression we have already seen here, A of Z has this expression which I have written on the bottom. So for that to be 0, the possible choice was J naught of Z is equal to G1 of minus Z. I call this equation 2, and J1 of Z is equal to minus of G naught of minus Z. I'll call this equation 3. Okay, okay, so you can verify, like if I relate my synthesis filters J with the analysis filters G as follows, as I have labeled in equation 2 and 3, then this A of Z term vanishes. You can easily see it mathematically. And now additionally, we are given in the question that we are using QMF. See, we have taken care of aliasing cancellation, fine, and now we are also using quadrature mirror filters. So for QMF, using QMF, the QMF constraint, remember that we in the previous question also we draw this diagram here. You see this, if H naught of Z is one filter, then the other one has to be H naught of minus Z. So this QMF constraint imposes another constraint, which is G1 of Z should be G naught of minus Z. Okay, and I'll call this equation 4. Okay, Right. So now what we can do is you we can combine this equation 2, 3 and 4 and claim that. So from equation 2, 3 and 4 we have J naught of Z. So we can basically relate both the synthesis filters J naught and J1 in terms of a single analysis filter G naught. That's what I am saying, because we have the relation between the two analysis filters G1 and G naught in equation 4, and then so we can overall relate both the synthesis filters J naught and J1 in terms of a single analysis filter, which is G naught of Z, and that relation is for J naught of Z, it's the same as G naught of Z, and J1 of Z would be minus G naught of minus Z. Okay. Okay, so now, okay, if J naught of Z is G naught of Z, I can also then write J naught of Z as, so what is G naught of Z? You go back to equation 1. So here I have written G naught of Z, you see this. So you now just substitute, okay? You just substitute the expression for G naught of Z. So that gives you, that gives you the expression for J naught of Z in terms of E naught and E1. So this is E naught of Z squared plus Z inverse E1 of Z squared. Okay, and similarly J1 of Z you are going to get is, okay, what changes we have to make? We have to replace Z by minus Z and also add a negative sign in front. So that gives you minus. So this negative sign I will just keep outside a bracket, and inside we have E naught of Z squared. So that even if you replace Z by minus Z, it remains the same. And we had a delay term plus Z inverse. So if you replace Z by minus Z, it becomes minus Z inverse, and the second square term again remains unchanged. Okay, this. Okay, so which is nothing but minus of E naught of Z squared plus Z inverse E1 of Z. Okay, we arrived at, and how did we get this last step? So this I have basically used equation 1. I have just substituted the expression of G naught of Z from equation 1. Okay, so the final form, okay, I'll just enclose it in a box. J naught of Z is E naught of Z squared plus Z inverse E1 of Z squared, and J1 of Z is minus E naught of Z squared plus Z inverse E1 of Z squared. This is my, these are my two synthesis filters. Okay, and if you check the options, see both option A and C are correct, which means actually option D, because option D tells both A and C are correct. So yeah, option D is the right answer, both A and C. both A and C. Okay, see, all the problems are straightforward. So now moving to the fourth one. Okay, what is the condition for perfect reconstruction? Okay, so you can straight away tell me the answer for this one. So would you like to tell the answer for this, Bharat? Yes, this one, the fourth one. What is the condition for perfect reconstruction? It's actually a follow-up question for the previous one actually. Yes, yes, hello. Okay, I don't get any response. Um, Not sure if people are there. Anyways, so I'll continue. So this, we are in the fourth one. Okay, so condition for perfect reconstruction. Okay, so x hat of z is, we saw in the previous question that x hat of z is your p of z times x of z plus a of z times x of minus, and this was your signal term, and this was your alias term. Okay, and for perfect reconstruction means that from x hat of z or x hat of n in the time domain, you are able to perfectly reconstruct your original input sequence, which is x of n. Okay, that's what perfect reconstruction means. And for that, anyways, you have to remove this aliasing component here, which is x of minus z component. Anyways, you have to get rid of that, so you have to ensure that in the first step. So for perfect reconstruction, that's the first thing you have to take care of. So for perfect reconstruction, this a of z has to go to 0, because I only want x of z component, right, in the first place. So a of z is 0. So this is nothing but alias free constraint or aliasing cancellation constraint. Okay, now if a of z becomes 0, then I basically have a simplified expression. So the second term basically vanishes. So what do I have? X hat of z, it's nothing but t of z times x of z. Fine. Okay, okay. And if I call this as equation 1, let's say, so the condition is that in general, if you deal with signals and systems, um, if we want to recover a signal from another signal, okay, let's say we have some x of n as our original signal, and it underwent some transformation to become x hat of n. That's what is happening in the block diagram as well. So if this modified signal, new signal x hat of n is a scaled and shifted version of your original signal x of n, then we are able to recover. Okay, that's usually happens in the LTI systems, right? If you have a scaled and shifted version of that original signal, then we know, then we can just undo those operations. We can shift it further in the opposite direction, and we can also scale it appropriately, or attenuate appropriately rather, to eliminate that scaling factor, and we can arrive at our original sequence. And this would involve some basic operations, right? Time shifting and time scaling only. So basically a delay block or a advanced block you would need, and also a multiplier, or a basically a multiplier scaling factor. Okay, so that is that. Yeah. Now so that's the point here. So for perfect reconstruction, what we want is, for perfect reconstruction, again I will write, okay, yeah, uh, you can unmute and let me know. You have raised a hand. So what's the concern? Yeah, you can talk to me. Yes, Bharat. Yes, you can turn on your microphone and you can speak if you have any questions.
No, sir.
Oh, because I just got a notification that you just raised a hand just now, multiple times.
By default, should.
Okay, okay, okay. Okay, so for perfect reconstruction, what we want is x hat of z to be of some form c times z to the power n naught into x of z. Okay, where c is a constant, some scaling factor. Okay, and this I'll label as equation 2. Why this form is needed? Because this actually translates to a form in the time domain. If you take the inverse z transform on both sides of equation 2, you will obtain that x hat of n is nothing but some c times x of c times x of, sorry, c times x of n minus n naught. So that's what I was saying actually. We have a scaled and shifted version of the original input sequence, and from that we can recover back x of n. Basically you need to multiply it by 1 by c, and of course I'm assuming that c is not 0, and then you can actually uh, advance it by a unit of n naught, so that gives you back x of n. So this is basically a scaled and shifted version of input. Okay, So this is what you need, and for that x hat of z should be of that form. And now if you compare equation 1 and 2, so from equation 1 and 2, if you compare, what can you say about the nature of t of z? It is clearly, so I'm comparing these two equations, this one and this one. So what can you say about t of z? It has to be of the form c times z to the power minus n naught. Okay, so this is another constant, and in the options actually this constant is chosen to be 1. Basically in option B you see, firstly option A is correct because a of z has to be 0. We have already argued that previously, this condition, this one, right? So that definitely has to hold. And in option B, t of z is z to the power minus n naught, which is actually of this form, which is a special case of this form corresponding to c equals to 1. So putting c equals to 1, we get t of z as z to the power minus n. Okay, so that option is also correct, and option C is not correct. Option C says a of z is of the form z to the power minus n. No, a of z has to be 0 because we have to get rid of the aliasing component. So both A and B are correct, which means option D. Both A and B are correct. So answer is option D. Both A and B. Okay, fine. Now let's move on to the next one. Let's move. Okay, this is the fifth one. Read the question. So in the fifth question, we have a signal x of n equals to pi by 2 times sine of 2 pi n by 8, and which of the following is true about the 8-point DFT, discrete Fourier transform of the signal? Okay, it will have, option A says it will have only it will only have frequency components at 2 pi by 8 and 14 pi by 8. Second option says all DFT components are non-zero, and similarly we have option C and D. Okay, okay, so yeah, so how do we do this? Okay, one naive approach could be, okay, we are given an input signal x of n, and we are asked to comment about its what is true regarding its 8-point DFT. So we are familiar with the formula for 8-point DFT. In actually multirate, we have seen DFT as a filter bank, but in general there is a explicit formula. So we can use that formula and find the DFT coefficients, which is denoted by capital X of k. Remember, k running from 0 to capital N minus 1. Here capital N is 8 because there is 8-point DFT. So we will have 8 such coefficients. So, but that will take a lot of time. That's one naive approach. Definitely you can do that and check like which components are basically existing, which of the following frequency components are existing, and you will observe that only a subset, only some of the components are actually existing. The remaining DFT coefficients would vanish, would be 0. So that's one way, of course, but in your exam you must be efficient and be quick in solving. So there's another way to uh, look for the right answer here. So the thing is, the observation is that instead of calculating the computing the DFT coefficients, what we will do is, okay, we are given the input signal, that's fine, x of n is given. Now, in order to comment about the DFT coefficients, I can also use the idea of inverse DFT. What inverse DFT does is it actually is an expression for your input signal only, x of n, in terms of your DFT coefficient. So now you are going back from the frequency domain to your time domain. So I'll note down the expressions, don't worry, but that inverse DFT relation you can use. Okay, and the key observation here is that x of n has a particular form here, pi by 2 times sine of 2 pi n by 8. Now it's a sinusoidal signal, and you can also express sine 2 pi n by 8 as e power j 2 pi n by 8 minus e power minus j 2 pi n by 8 whole divided by 2j. And once you do that, you already have an expression which expresses the input signal in the form of an IDFT expression, right? So once you do that, you can automatically find, okay, which of the terms are existing, and basically it will comprise of two exponential terms, right? It's a sinusoidal sequence. That's why only two DFT coefficients are actually non-zero. That is the key observation here. What are those two DFT coefficients that we have to actually we have to compare the frequency components, and we can argue that, okay, the DFT coefficients at these frequency components are actually surviving and the rest of them are all zero. So mathematically we can do that. Okay, that's all. That's the key observation here. You don't need to explicitly work out and calculate all the DFT coefficients and check. That will take you a lot of time. So yeah, so that is the idea here. So fifth question. First things first, I'll just review a basic, the formulas and all for the endpoint DFT as well as the IDFT, because IDFT is the one which we are using here. So first of all, the endpoint DFT of any signal x of n is defined as capital X of k is equal to summation small n running from 0 to capital N minus 1 x of n e power minus j 2 pi k n by capital N. That is the form, and where k runs from 0 1 till capital N minus 1, and also small n runs from 0 1 till capital N minus 1. These terms, actually these capital X of k, are your DFT coefficients. So for an n point DFT, you would have capital N such DFT coefficients. Fine. Now, as I mentioned, we can also express the inverse DFT, okay, also the n point inverse DFT or IDFT is defined as, now you are going back to the time domain, x of n, you are expressing x of n in terms of your DFT coefficients, just the reverse way. So that becomes 1 by capital N factor is present, and you have a summation. Now the summation index is k, okay, 2n minus 1 capital X of k inside the summation multiplied by, previously you had e power minus j 2 pi k n by capital N. Now that minus will go away, so you will have e power j 2 pi k n by capital N. That's generally, whenever you do an inverse transform, let's say a basic DTFT also, when you take DTFT and when you take IDTFT, so this changes happen, right? So from time to frequency and vice versa, from frequency to time. So these factors, exponential factors, undergo a change of sign and so on, right? Okay, so fine. So this now, again, k and n still run from 0 to capital N minus 1. Okay. Okay. So we will actually use this endpoint IDFT for our problem. And firstly, if you go back to the question, we are asked about the 8-point DFT. So which means capital N is 8. So here capital N is 8 because we are dealing with 8-point DFT in our question. So therefore, straight away you can actually substitute capital N equals to 8 in this equation here for IDFT. So that will give you 1 by, now capital N becomes 8 summation k running from 0 to 7 capital X of k e power j 2 pi k n by 8, right? And here k runs from 0 1 to n minus 1, which means 7, and n also runs from 0 to 7. Fine. Okay, so now for the sake of more clarity and completeness, I'll expand this summation so that you are able to observe it even more clearly. Okay, we don't need to, but still I will. So this means X of n is 1 by 8 is the factor sitting outside, and if you expand this you will have 8 terms, right? First term would be for k equals to 0, which is x of 0. Second term would be capital X of 1 times e power j 2 pi n by 8. So this is for k equals to 1. Similarly, for k equals to 2, you will have e power j 4 pi n by 8. X equals to 3, sorry, k equals to 3, you will have this term, sorry, 6 pi n by 8. Okay, then for k equals to 4, you would have j 8 pi n by 8, which is nothing but e power j pi n, plus for k equals to 5, now you will have j 10 pi n by 8. Then for k equals to 6, you have this term, And finally, the last term would be for k equals to 7, that's the upper limit, this. Okay, now let me call this as equation 1. These are the 8 terms inside the, if you basically expand the summation. Fine. Now in our question we are given x of n. What is x of n? Go back to your question. This is pi by 2 times sine 2 pi n by 8. So this is pi by 2 times sine 2 pi n by 8. This is pi. Okay. Now as I mentioned, so in equation 1 you see that you have a form. So this capital X, x of 0, capital X of 1, these are your DFT coefficients, right? This could be in general any complex number, right? So that's a scalar, basically that's a complex scaling factor, that's a scaling complex number in general. And with that, the form of this x of n in equation 1 is that, okay, you have a complex exponential of the form e power j something, j omega n, like omega is varying, right? If we are undergoing a shift in the frequency, the first term is at 0 frequency, x of 0 plus x of 1 times e power j 2 pi n by 8. So there are terms involving this e power j some omega in this form, right? And we have some of such terms. So that's why the step which we are going to do is we are going to express our given input signal in the same exponential summation form. Okay, so this sine 2 pi n by 8, you can also rewrite it as e power j 2 pi n by 8 minus e power minus j 2 pi n by 8 whole divided by 2j. This you know, right? This formula. Okay. Or in other words, you have x of n is pi by 4j e power j 2 pi n by 8 minus pi by 4j e power minus j 2 pi n by 8. Okay. Fine. Now you see in equation 1 we also have a similar pattern. We have some e power j 2 pi n by 8 or 4 pi n by 8 with some scaling factor and added up together. So here also we have two such terms. Okay, but the second term in this equation here, the frequency is negative, minus 2 pi has a negative sign, e power minus j 2 pi n by 8. But in equation 1 neither of those terms have a negative sign there. So we have to adjust for that negative sign here in order for the two forms to be similar. Okay, so what we will do is so we can actually rewrite this as, in order to take care of that negative sign, remove that negative sign, what we will do for this second term here is that is pi by 4j e power minus 2 pi n by 8, and now I can also multiply this by e power j 2 pi n. Yes or no? I can also multiply, because essentially what is e power j 2 pi n? This is simply 1, because if I what is e power j 2 pi n? e power j 2 pi n is nothing but cos 2 pi n plus j times sin 2 pi n. So this is really Euler's theorem. And now n is an integer, right? N is in discrete time, n is an integer. So if n is an integer, then cos 2 pi n, this term becomes 1, and sin 2 pi n for any integer value of n, this goes to 0. So this is overall 1. So e power j 2 pi n is 1. So I can multiply any quantity with 1 and it remains unchanged. So that's fine, that's allowed. So I'm making this adjustment here. And now what this does is, this is the first term, and the second term now I can rewrite it as pi by 4j. This overall, if you just, okay, it's a product of exponents, therefore the powers get added, right? So product of two exponential terms, complex exponentials, is basically e power. The overall power is sum of the two individual powers. So if you do that, you get e power j 14 pi n by 8. Okay, so now we have removed that negative sign, you see, and if you call this as equation 2, and now you're done, you can compare this equation 2 with equation 1 here. And what can you observe here? Excuse me, just okay, yeah. So now you can compare equation 1 and 2, and you see that these two frequency terms, e power j 2 pi n by 8 and e power j 14 pi n by 8, both are present here in equation 1 also, which actually corresponds to your which terms? This one. This is e power j, so maybe e power j 2 pi n by 8, and this one is your, maybe I'll circle it, wait, maybe this term, how can I get this term? Maybe I'll just enclose it in a dashed circle. So this term, this is one term for the frequency e power j 2 pi n by 8, and we have our last term which has the frequency 14 pi n by 8. These are the two terms which are actually present effectively. So you can argue that all the remaining coefficients of DFT, which is capital X of 0, capital X of 2, capital X of 3, capital X of 4, capital X of 5, and capital X of 6, they are all 0. They all vanish. So there would be no contribution from the remaining terms, right? So you see, that's how we were not required to compute the individual coefficients separately. Okay, so now by comparing equation 1 and 2, we get, so if you compare the two equations, okay, the term corresponding to e power j 2 pi n by 8 is this one, okay, and what is the scaling factor for that term? Capital X of 1, but there is also a factor of 1 by 8 sitting outside. So that a capital X of 1 by 8 would be the same as this pi by 4j. Okay, so I can write, the first observation is that capital X of 1 is capital X of 1 by 8 is the same as pi by 4j. Okay, or which gives me basically, or I can write here, which gives me capital X of 1 as 2 pi by j. Okay, and I also get, if I compare the next term, which is the term corresponding to the frequency 14 pi n by 8, which is this last term here. So the coefficient for that term is x of capital X of 7, and also I have a factor of 1 by 8. So with that has to equate to minus pi by 4j. So for that I'll have x of 7 by 8 should be equal to minus pi by 4j, which gives me capital X of 7 is minus 2 pi by j. Okay, and for all the other DFT coefficients, they go to 0. They are basically 0. Their contribution is 0, because only we have two effective terms here. Okay, so this all other terms are 0. Okay, so maybe I'll write it, this and this these are the two surviving terms. Okay, that is the observation. Okay, now change the color. Okay, now we are done. So this, and for all other, meaning that x of 0, x of 2, x of 3, x of 4, x of 5, x of 6, they are all 0. Okay, so only the x1 of a capital X of 1 and a capital X of 7, these are only present, which means that only non-zero coefficients are x of 1 and x of 7 at frequencies of, for x of 1 the frequency component was basically this 2 pi by 8, right? 2 pi by 8. And for the x of 7, the last term, the frequency was 14 pi by 8, right? So these two components are located at frequencies of 2 pi by 8 and 14 pi by 8 respectively. Okay, only these two are contributing. These two coefficients are non-zero. Otherwise, all the remaining coefficients are 0. So yeah, so that's exactly your option A, right? It will only have frequency components at 2 pi by 8 and 14 pi by 8. So that's your option A. Okay, fine. So now okay, Now the sixth one, six, seven, these are just one line questions. I'll quickly go through them. So in the sixth question, you have to design a multi-rate low pass filter, and the specifications are given to you. The pass band should be from 0 to 50 hertz. Okay, here the frequency is in hertz. Okay, and the stop band should lie from 60 hertz to 280 hertz. And the stop band deviation, remember we saw the uh, stop band, error criteria, some phi 2. Similarly for pass band we had phi 1, right? These criteria. So stop band deviation should be the maximum, basically it's the maximum deviation of the ripple that you can allow from the ideal uh, filter in the stop band. So that's the stop band deviation, which should be 0.001. Similarly pass band deviation should be 0.01. And given that the sampling frequency fs is 400 hertz, what would be the value of normalized transition width? So this is a very straightforward, simple question. So in case you're encountering this word for the first time, normalized transition width, there's nothing fancy about it. So transition width, what does it mean? You know that in case of a filter, there are three regions, right? So we have for a low pass filter, we have a pass band, then we have a transition band, and then we have a stop band. So this transition band is the portion where my filter characteristics is switching from pass band to stop band. So that's your transition band, and the width of that transition band is basically your transition width, as the name implies. And normalize, this term normalize is present, which means that it is normalized with respect to your sampling frequency. That's it. So we basically have to normalize with respect to the sampling frequency fs. That's it. So I'll rewrite it. First of all, I'll just um, draw a simple rough sketch of a low pass filter. So what do you have here is something that looks kind of like this. Okay, and I can allow actually for some ripples here. So let me call this as the pass band edge. Basically that's your pass band frequency. So this, the the point till which the frequency response remains more or less flat is the pass band region. So this is your pass band. Okay, all these things you know. And this deviation actually is your pass band deviation. Okay, that's one of the specification that you need to keep in mind. This frequency here is your, let me call it f pass, which means passed band frequency. This is 0.0. And similarly the point at which it almost goes to 0, this point is your stop band frequency. I'll call it f stop. Okay, and of course you can again allow for some, for practical purposes you can allow for some ripple like this, and like this. So that in the stop band will have some deviation like this. Maybe I should draw it properly. This much is your deviation. Okay, ideally it should be 0, but there's some ripple existing in the stop band as well. So that's your stop band deviation. So, and of course this is your stop band. Okay, this portion in between, maybe I'll shade it. This portion this green shaded region is your transition band, and this width of the transition band is your transition width. Okay, by the way, this is f pass is your mention it here. F pass is your pass band frequency. F stop is your stop band frequency. Okay, great. So this is your what is meant by transition width. So mathematically, transition width is equal to delta f, which is nothing but f stop minus f pass, the difference between stop band and pass band frequencies. So transition width of a low pass filter. And the term normalized transition width so we are scaling it appropriately, and normalized transition width means we are normalizing with respect to our sampling frequency fs. Okay, so where fs is the sampling frequency and this is in hertz. Okay, this is the definition of what is normalized transition width, okay, for a low pass filter. So now okay, so this in our question, I'll write here what is the pass band specification. The pass band, so although in the question these pass band deviations, stop band deviation are given, but for finding the value of normalized transition width, we don't really require those parameters. We just need this f pass and f stop and the sampling frequency by definition. So the pass band, if you see, it's from 0 to 50 hertz. So pass band is from 0 to 50 hertz as per our question. So that automatically implies that your pass band frequency would correspond to the point 50 hertz, right? Just from the diagram you can clearly say that. And similarly the stop band, if you go to the question, is from 60 to 280 hertz. Okay, 60 to 280 hertz. Sorry. Okay, so this is from 60 to 280 hertz, which means again from the figure your stop band frequency would be 60 hertz, right? It starts from that point. The stop band starts from 60 hertz onwards. So this is 60 hertz. And the sampling frequency is also given. Sampling frequency denoted by Fs. If you go to the question, it is given as 400 hertz. So this is 400 hertz. This is also given. Okay. Okay, all these things are given. So these were the given information in the question, and so now we can put it in the formula basically. First we can find delta F, which is nothing but the difference between the stop band frequency and the pass band frequency, which in our question happens to be 60 hertz minus 50 hertz, which is 10 hertz, right? And therefore the normalized transition width is delta F by Fs, which is 10 hertz by 400 hertz. It's nothing but 0.025, and it is dimensionless because it is normalized, right? So 0.025 is the answer, and that corresponds to option A. So answer is option A. Great. Okay, now just quickly we're going to go through. Okay, I think we are in the seventh one. Okay. Okay, the seventh one, it's just, you can straight away even tell the answer as well. So what is the pass band frequency for a 2-channel quadrature mirror filter bank if the stop band frequency is 0.525? Okay, this was again discussed in the lectures. So so this is QMF, right? Quadrature mirror filter bank. So for that, what is the structure of a QMF? There's a QMF pair, you remember, and it's a 2-channel, so there are 2 filters. So if the first one is H naught of Z, let's say it has this kind of a trait. Okay, of course you can allow for some ripple here in its stop band, and then the other one, so this, if you call it as H naught of Z, okay, then its pair, its counterpart for QMF would be pretty much symmetric, like this. Okay, yeah, approximately like this. And this point about which, so this red filter is nothing but the shifted version of H naught of Z by pi units. So this is H naught of by pi frequency. So this is this, and this point about which the symmetry exists, we know that, okay, this point is your quadrature frequency, right? This point corresponds to pi by 4, sorry, pi by 2, because it is the quadrature frequency, 1/4 of 2 pi, 1/4 of the sampling frequency. Okay, now the thing is, this one, till this point the first filter, okay, maybe just a second. Okay, so this till this point, this blue dashed line, this till this point H naught of Z, the first filter, had a flat response, so this corresponds to its pass band frequency, this point, okay. And similarly this one, this red filter, and this point corresponds to the um, stop band, right? Omega s, omega s, I'll use omega s, and maybe I'll stick to the colors only. So this pi by 2 I will denote it by green color, okay. Fine, this is the picture we have, and of course these points are starts at 0 and it ends at pi, okay. So I hope you are able to visualize this, right? The passband frequencies and stop band frequencies of these two filters, so the passband for the first one becomes kind of a stop band frequency for the other filter, and vice versa, so that way, okay. And they're symmetric about the point pi by 2, and that's the main thing. So by symmetry around pi by 2, which actually is the case that is satisfied for QMF, what can you say? Okay, you can say that this gap, since there is a symmetry about pi by 2, this gap and this gap both are same. Or you can also say that, okay, this much is the same as this much, okay. In both ways, if you just follow, what you will get is by symmetry omega p is pi minus omega s. So, and now in our question omega s is, I think, given, omega s is given to be 0.52 pi, this is given. So therefore omega p is clearly pi minus 0.52 pi, which is nothing but 0.48 pi. So of course your answer is, I think that's option B. In option B we have 0.48 pi, this one. And coming to the last problem for today, okay. For the last one, let me solve it anyways. Okay, so which of the following is not suitable either as a low pass or as a high pass filter? Meaning that which of the following conditions or criteria for the filter makes it not suitable for neither suitable for a low pass filter nor suitable for a high pass filter. That's it. The conditions for the filter are given in the options, whether h of n should be even symmetric and of odd length, even symmetric, even length, and so on. So you can solve it generally, but what I will do is I'll take some examples, illustrate with simple examples, choose some filters, arbitrary filters, and check whether it satisfies the constraint or not. Okay, so let's do that. Okay, so basically this is what a low pass filter looks like, right? This is an LP. It starts at 0. Okay. This is an LP. And what does a high pass filter looks like? So the low pass filter basically passes all the low frequency components. This is your omega axis. This is your h of e power j omega, right? And the high pass characteristics, the high pass filter would pass only the high frequency components. So it will block the low frequency components and then it will pass the high frequency component. So maybe at pi it is passing, okay? And this low pass will actually reject all the high frequency components and pass only the low frequency. Fine. And okay, this is your high pass filter. We know this. So in our question we are asked which of those conditions is not suitable for LPF as well as HPF. It can neither design a low pass filter nor a high pass filter. So essentially LPF can't be designed, HPF can also be can't be designed as well. So if you combine these two conditions, so what happens in low pass filter? See, for omega equals to 0 or low frequencies, it should pass, right? It should have a transfer function which should be non-zero. That's for a low pass filter. So for a low pass filter, the frequency response h of e power j omega at omega equals to 0 is non-zero. That's why it is passing it, right? Those are low frequency components. And similarly for a high pass filter, it is passing the frequencies which are higher. Okay, the high frequency components are being passed, which means for a high pass filter the frequency response h of e power j omega at omega equals to, let's say, pi, which is a high frequency, that should be not zero, right? And now in order for a filter to not satisfy either of these two criterias, okay, both of these evaluations at omega equals to 0 as well as omega equals to pi, they should be 0, right? Because individually for a low pass filter the condition is non-zero at omega equals to 0, and similarly for high pass filter it is non-zero at pi. So a filter which is neither a low pass filter or a not a high pass filter must satisfy we need the frequency response at low frequency to go to 0, and also the frequency response at high frequency like pi to go to 0 as well. So it's neither a low pass nor a high pass. You understand, right? So that is the key observation. So now let's do a case by case analysis. So case A, this is corresponding to your option A. So option A, what does it tell is h of n is even symmetric and of odd length. Okay, h of n is even symmetric and odd length. An odd length, if you go back, odd length means order should be even because the order is one less than the length. So if length is odd, order is even. Now we have already captured all this information in our very first question in a tabular form. For an even symmetric impulse response and even order, the type of the filter, type of linear phase FIR filter is a type 1 filter, right? Because if you go back to the first question, we started with that, with this table. This is type 1, even order, even symmetry. So exactly that thing. So yeah, so that means that is a type 1 linear phase FIR filter. So option A is a type 1 linear phase FIR filter. If this doesn't qualify, we have to check if this is not qualifying either as a low pass filter or a high pass filter. That we have to check. Now we can take a simple example. Okay, one example for such an impulse response which is even symmetric as well as of odd length could be, let's say, length is odd. That means we can take a filter of length, let's say 3. 3 is an odd number and it should be even symmetric. So one possibility could be, this is I have chosen 1, 2 and 1. You see, even symmetry is there, and let me call this at index 0, and also the length is odd. So the length is 3, which is odd. Okay, now if you visualize it, what does it look like? Sorry. Looks like this is h of n. We are plotting h of n. So it looks kind of like this. Only 3 samples, 3 coefficients are there. This is at 0, 1, 2. This height is 1, this height is 2, this height is 1. So this is clearly even symmetric and of odd length. Now its frequency response, if you calculate, frequency response is nothing but the DTF, discrete time Fourier transform of h of n. If you calculate that, which is capital H of e power j omega, so we know that it is h of n e power minus j omega n summation over n, and here small n runs from 0 to 2 because we have taken a length 3 sequence, right? So what are you going to get? You can calculate. This would be 1 plus 2 times e power minus j omega plus e power minus 2j omega. Great. Now going back to our condition that we need to check. These two conditions. Maybe I'll just put them in a box. This green box encompasses the two conditions that we need. First of all, we need this, and also we need this. Okay, let's see if they are getting satisfied or not. So for this case, so first thing is to evaluate the frequency response at omega equals to 0. What does that give you? That will give you 1 plus 2 plus 1, which is 4, and this is clearly not 0. So of course this is not 0, so we can't say that okay, it is not suitable for a low pass filter. In this case you can use this filter particular case to use to to design a low pass filter because it is not zero. So clearly that is the condition which we need is not satisfied. So we don't even need to calculate evaluate this frequency response at omega equals to pi. It's not even required. So this case A doesn't work. Case A doesn't work. Okay, therefore not, like, what should I say, therefore doesn't work. So the first constraint itself fails here, so it doesn't work. Now I'll go to the next case, which is case B, corresponding to option B. What does it tell me? H of n is even symmetric and even length. And even symmetric and even length means odd order, which corresponds to your type 2 linear phase amplifier filter. So H of n is even symmetric and even length, which means odd order. This corresponds to type 2 linear phase FI filter. We also have uh, mentioned it in our first table, basically the table that we have drawn. The second row was corresponding to type 2, which has this set of properties. So one such filter, an example, we will again take an example for this simple example. So here the length is even, so we can choose the length to be 4, which is an even number, and again it is even symmetric, so I can have a sequence of this form 1 2 2 1, right? And let me call this as the origin, n equals to 0. So clearly here the length is 4, which is even, fine. And if you observe how h of n looks like in this case, so this is n. At n equals to 0 you have value 1. At n equals to 2, sorry, n equals to 1 you have value 2. At n equals to 2 you have value 2 again. At n equals to 3 you have value 1. So this is even symmetry, right? Okay, again let's find the frequency response or the DTFT. So this is h of n e power minus j omega n running from 0 to 3 here, it's length 4. That will give you 1 plus 2 times e power minus j omega plus 2 times e power minus 2 j omega plus e power minus 3 j omega. I hope I have not made any calculation mistake here. Yeah. Yeah. This is what you are supposed to get, and again we'll check the criteria. Okay, e power j omega at omega equals to 0 we will calculate first. If you do that, what happens at omega equals to 0? All these e power j omega terms basically become 1. So you'll have 1 plus 2 plus 2 plus 1, which gives you 6. And again this is not equals to 0. So this can be used to synthesize a low pass filter. Again, this first constraint itself fails here. We don't even need to check the other constraint at omega equals to 5. So again this, therefore this also doesn't work. Okay, now similarly we will check the third case, case C, which is option C. It is h of n is odd symmetric and odd length. So let's see, h of n is odd symmetric and odd length. An odd length automatically implies even order. So this corresponds to your type 3 filter. So I'm writing all these things uh, in this document so that you can later revisit it and understand it properly. So that's why I'm putting so much time in writing all these things. So this is the type 3 case. So let's check this, and again let's come up with an example, simple example of such a filter. Okay, firstly I should have odd length and odd symmetry as well. So odd length, if I choose the length to be 3, and if I have a filter of the form, let's say 1 0 minus 1, okay, and let me label this at n equals to 0, this point. Okay, so clearly this chosen filter has length 3, which is odd, satisfies our requirement, and also if you visualize it, it has got a odd symmetry. So at n equals to 0, it has the value 1. At n equals to 1, it has value 0. And at n equals to 2, it has value minus 1. So you see there is a odd symmetry or anti-symmetry here. And we need this 0 value at the center so that this anti-symmetry property is satisfied or odd symmetry is satisfied. Okay. Now again finding the frequency response. This is summation h of n e power minus omega n running from 0 to 2 because there are 3 samples. So that gives you can calculate so the second term will basically vanish because the filter coefficient at n equals to 1 is 0. So there will be only two terms will be there. So the frequency response would be of this form, 1 minus e power minus 2j omega. And now let's check our two constraints. So let's evaluate the frequency response at omega equals to 0. That will give you 1 minus 1, which is 0. So you see this becomes 0. So clearly low pass filter can't be designed. That's fine. We can't design a low pass filter with that. So the first constraint is cleared, satisfied. And what about the next constraint, e power j omega, this frequency response at omega equals to pi, you have to evaluate. The frequency response at omega equals to pi, what happens? 1 minus e power minus 2j pi. What is the value of this? So you see e power minus 2j pi is the same as it's basically e power minus 2j pi is 1 because e power minus 2j pi is cos minus 2 pi minus j sine 2 pi, and cos minus 2 pi is the same as cos 2 pi, which is 1, and this term is 0, so this is 1. Okay. Okay, so this is 1 minus 1, and again this also goes to 0, so therefore we can't design a high pass filter as well. So both the constraints that we needed in this green box are satisfied. Both the constraints are satisfied. So option C is the right choice. So therefore this works. Okay, and automatically you can anyways check the remaining case, the other case, which is like case D. That will fail, that will again fail. The fourth case, I'll do it anyways. So the fourth case tells you odd, symmetric and even length. So we already got our correct answer, which is case C, which corresponded to odd, symmetric and odd length. That is the one which can't. If you have a filter, if you have an FIR filter, if linear phase FIR filter with odd symmetric impulse response and odd length, then it can't be used to design a low pass filter or a high pass filter. That is your observation. Okay, and now coming to the last case, anyways, just for completeness, we'll check this case as well. So this tells me h of n is odd symmetric and even length. Even length again means odd order, and this is nothing but your type 4 linear phase FIR filter. Okay, now okay, so we need odd symmetry and even length. So again I will choose an example. So I'll go to the next page. Odd symmetry and even length. So an example could be even length. Let me take the length to be 4. So there will be 4 samples. So 1, 2, minus 2, minus 1. I can choose a sequence like this where my length is even. Length is 4 here, which is even. Okay, and if you plot the impulse response, at n equals to 0 you have the value 1, at n equals to 1 you have the value 2, at n equals to 2 you have the value minus 2, at n equals to 3 you have the value minus 1. So this is your h of n. So you see clearly there is a odd symmetry that exists here, or an anti-symmetry, correct? So now if you find your frequency response again, we'll check those two conditions if they are satisfied or not. So here n runs from 0 to 3, h of n e power minus j omega n is minus. So that gives you, from this figure actually you can write it as, there will be 4 terms because there are 4 non-zero coefficients, so there will be 4 terms. Yeah, you should get something like this. Now the last step is to check these two conditions. First we will evaluate at omega equals to 0, we will evaluate the frequency response at omega equals to 0. that will give you, okay, that cancels out, so that gives you 0. So that is fine. The first condition is satisfied, so I can't design it design any low pass filter using this. So the first condition is met, but the second condition, which is evaluating the frequency response at omega equals to pi, what does that give me? 1 plus e power minus 1 plus 2 times e power minus j pi minus 2 e power minus 2 j pi minus e power minus 3 j pi. And this, if you calculate, it is 1 minus 2 plus 1, which is minus 2, and clearly this is not equals to 0, so this is not vanishing. So the high pass filter constraint doesn't work here, so this also fails, therefore doesn't work. Okay, the only uh, condition that works actually is the case C, which was odd symmetric impulse response and even length filter. Sorry, odd length filter. This one, this case C. Even sorry, odd symmetric impulse response and odd length filter. This one works. So okay, so the correct answer was option C. Okay, we have spent a lot of time in each of the question. I hope it was clear, and with this we have come to the end of today's session. We have already taken a lot of time, but the point was to convey, all the things clearly. I hope you get the idea. And so yeah, we can stop the recording now, and we'll meet again on next Tuesday. If you have any questions, you can ask me, or else I'll just stop the recording and end the call.
No, sir, no questions.
Okay, I'll let me stop the recording.